Sorry for that one. I just closed the door. I will close the other door also. Good morning, Los Angeles. It's January 30, 2022. It's afternoon here in Los Angeles. Okay, this is David de los Reyes. I will now be discussing a new topic on my channel for today. Okay, I will check my calendar. It's fine. I am now on lesson number 21 on the topic integral calculus on my channel. So for those people who are studying integral calculus, this is for you guys. Okay, let's proceed with the discussion for this afternoon. This is not a viral video, this is educational, so it's up to you to analyze what's better for you guys. It's some other things, you like it, but you should like also my channel. I will assure you that you will get something from it. Okay, let's proceed. My topic for today is integration of inverse trigonometric functions. Yesterday, I gave you the two formulas for taking the integral of inverse trigonometric functions. Number one is the arcsine, and number two is the arctangent. Okay, so for today, I will give you examples for those two formulas. Okay, let's proceed with example number one. Example number one is the integral of dx over the square root of 16 minus x squared. Okay? If we try to observe the given problem, it seems this is similar to the form, okay, to the form the integral of dv over the square root of a squared minus b squared. It seems they look alike. So if they look alike, when we integrate this one, this should be the answer. That's the formula I gave you yesterday. The integral of dv over the square root of a squared minus b squared equal to arcsine of b over a plus c. Okay, let's do the verification for us to use this formula. Okay, from the given problem, 16 is a square, right? And the b is actually, b square is x square. The sign inside is negative, right? So if a square is 16, take the square root of both sides. Raise both sides of the equation to the 1/2. Okay? 2 times 1/2, it will now just be simply a to the first power, or just simply a. 16 to the 1/2 is the square root of 16. It could either be plus or minus. Okay? So I will just place for the solution here a equal to 4. Okay? I will use the plus sign. Okay? From the given problem, the value of b squared is x squared. Same. Take the square root of both sides. Right? b squared raised to 1/2. These two here cancel with this. Left hand side will just be simply b to the first power, or just simply b. X squared raised to the 1/2 again. 2 cancel with this. It will just be simply x to the first power, or just simply x. Meaning b is equal to x. Take the differential of both sides. db equal to dx. It is exact. It is exact. Right? So as per our verification, dv is exact, or dx is exact. We have computed already for the value of a, and that is 4. Plus 4, or simply 4. Therefore, the integral of dx over the square root of 16 minus x squared As per verification, it falls under arcsine of B over A plus C. So the final answer, it will be arcsine. What is B? It is X. And what is A? It is 4. This is plus C. That's the final answer. As simple as that one. Okay? I will repeat it for the last time before we will proceed with example number 2. The integral of dx over the square root of 16 minus 4x squared. Similar to this form here, so the answer should be arcsine of B over A, which is x over 4 plus C. That's the final answer. Okay, let's proceed with example number 2. Example number 2, it will be a little different, okay? Example number 2, the integral of dx over 3 plus 2x squared. Okay? But it looks similar to the arctangent. It looks similar to the form dv all over a squared plus b squared. And actually, this is under arctangent. The integration formula is 1 over a, arctangent of b over a plus c. But let us do the verification. If the value of b and a are exact. From the given problem, obviously the pure constant is the a square, right? So a square is 3. Take the square root of both sides. Or raise both sides of the equation to the 1/2. A square, raise that again to the 1/2. These two here cancel with this. Left hand side will just be simply a. Right hand side, 3 to the 1/2 is just the square root of 3. Meaning the value of a is square root of 3. It's not a perfect square. It is under the radical sign. That's why I place a equal to the square root of 3. And still from the given problem, the term with the variable should be b squared. Okay? So b squared is actually 2x squared. Right? 2x squared from this. Then take again the square root of both sides. B squared raised to the 1/2. These two here cancel with this. Left hand side will just be simply b. Right hand side, 2x squared raised to the 1/2 will be the square root of 2x squared. The operation inside is multiplication, right? So actually we could segregate. So the simplification of the right hand side, it could be the square root of 2 times x squared raised to 1/2. Okay? Okay? 2 is not a perfect square, so it is still under the radical sign. But x squared is a perfect square, and we are taking the square root of that because these two here cancel with this. So what will come out is just simply the right hand side is square root of 2 times x. Okay? This is square root of 2 times x. Okay? Let's compute for the value of b. Take the differential of both sides. The differential of b is just dv. The differential of the right hand side is a constant in the function, so it should be that constant times the differential of the function. The given function is just simply x, so its differential should only be the x. Okay, not exact. Because from this, we don't have any square root of 2. So I place it here, it is not exact. But actually, there's no problem with that one because we could insert this one and we will place the reciprocal of this outside of the integral sign to solve for the problem. Okay, the final answer now, therefore, the integral of dx over 3 plus 2x squared is actually 1 over a. 1 over a, what is a? Square root of 3. Okay? Times the reciprocal of the square root of 2. 1 over the square root of 2. The integral of the given function. It now falls under arctangent, obviously, right? So 1 over the square root of 2, arctangent of b over a plus c. b is actually square root of 2 times x, right? It is this. And a is actually square root of 3. This is plus c. Okay? Actually, we could give this now as our answer, but actually we could still simplify. Square root of 3 times the square root of 2 is actually square root of 6. So the final coefficient of the answer will be 1 over the square root of 6. Arctangent of b, which is square root of 3 times x, all over the square root of 2, square root of 2x, all over the square root of 3 plus c. That's the final answer. So as you notice to solve the problem, we just verify the value of a and the value of db. And if it is not exact, we could do something for it to be exact. And if you did the correctness for the correction, you could integrate now by using the formula arctangent. So I will repeat it before we will proceed with example number 3. The integral of dx over 3 plus 2x squared, the final answer will be 1 over the square root of 6. It falls under the arctangent. Arctangent of b over a, square root of 2x all over square root of 3 plus c. That's example number 2. Okay, I'm checking my camera. Let's proceed with example number 3. It's a little different. It got a little variation from the first two. Example number 3, the integral of 2y dy over the square root of 1 minus 4y to the fourth. We got the radical sign here, and it seems this is similar to the form a squared minus b squared. Kaya I wrote it here, that's why I wrote it here, similar to the integral of db over the square root of a squared minus b squared. Okay? And the solution for that is arc sine of b over a plus c. Okay, let's do our verification. It's always verification. The integration is simple because we just follow this. But we must do the verification if the given values are correct or not. From the given problem, a square is this one here. A square is 1, right? Take the square root of both sides. A square raised to the 1/2, these two here cancel with this. Left hand side will just be simply a. 1 raised to the 1/2 is just the square root of 1. 1 is a perfect square. It could either be plus or minus 1, right? We will use plus 1. Okay? We will just only use a to be 1. Okay? From that verification. B square is actually 4y to the fourth. Okay? Then, say, to compute for the value of b, raise both sides of the equation to the 1/2. B square raised to the 1/2, these two here cancel with this, left hand side will be b. Right hand side, 4y to the 4th raised to the 1/2 is just the square root of 4y squared. The operation inside is multiplication, so this should be equal to the square root of 4 times y to the 4th raised to the 1/2. Okay, the operation is multiplication, we can segregate it. The square root of 4 is a perfect square. It could either be plus or minus 2 or this simply 2. Okay, y to the 4th raised to the 1/2, 4 times 1/2 is actually 2. So the square root of y to the 4th is y squared. That's why I place it here. The value of b is 2y squared. Right? Let's verify the value of dv by taking the differential of both sides. The differential of b is just dv. The differential of the right hand side, 2 is a constant, y squared is a function, constant times a function. So it should be 2 times the differential of y squared. It falls under the power formula. And u raised to n minus 1 times the differential. So 2 raised to 2 minus 1 or just simply y times dy. Power formula under differential. 2 times 2 is 4. So dv is 4y dy. Is it exact? It looks similar, but we got a 2 here. So what do? We bring out the 2. Okay? Then we take the reciprocal of this. Reciprocal of 4 is 1/4. The integral the complete differential as per verification is 4y dy all over the square root of 1 minus 4y to the fourth. And this now falls under this form here. And the solution should be arc sine of b over a plus c plus the little adjustment on before the radical, the integral sign. So 2 times 1/4 is 1/2 because 2 over 4 is 1/2. And the solution for this now, we just follow this. Arc sine, what is b? B is 2y squared. 2y squared over 1 plus c. Or final answer, since this is 1, it's no good if there's 1 over there. If it's 1, it's understood to be 1, right? So we just simplify our final answer. The final answer should be 1/2 arc sine of 2y squared is actually over 1, or 2y squared, same as this, plus c. Final answer for the integral of 2y dy over the square root of 1 minus 4y to the fourth is 1/2 arc sine of 2y squared plus c. It's easy. So the formula and how to take the integral, it's not complicated. The only problem is the verification of the value of a and b. You must have to compute for the value of a and for the value of dv and try to see if it matches this formula here. Okay, if it doesn't match, it's the wrong solution. If it matches, that's the correct solution. Okay, that's example number 3. Okay, example number 4, the last one for this afternoon, January 30. The integral of x minus 5 over x squared plus 5 times dx equal to. On the first look, we don't have any radical sign. Okay, any square root. So obviously this is not under arc sine. But it seems this falls under arctangent. But we must have to do something first before we could proceed for those. We got 2 numerators so in 1 denominator, so actually we could expand. This should be equal to the integral. We will take the first numerator divided by x squared plus 5. This is x dx over x squared plus 5. We just expand. And minus 5 dx over x squared plus 5 is, it's automatic. I bring out 5 already. Minus 5, the integral of dx over x squared plus 5. So after the expansion, it came out as 2 terms. And from the first equation, okay, it seems it's not under the arctangent. Okay, I think that's under the natural logarithm. So if this falls under the natural logarithm, the integral of du over u, okay, there should be u, right? The value of u is on the denominator x squared plus 5. Du will be, it is a sum, right? 2x dx plus 0, or du is 2x dx. It is not exact. It looks similar except for the value 2. So we are correct that this is under natural logarithm except for the value 2. But there's no problem with that one. We counter offset this one by placing the reciprocal of 2 outside the integral sign. So this is done. Okay, let's try to integrate the second one. Minus 5, the integral of dx over x squared plus 5. And it looks similar to the form, the integral of dv over a squared plus b squared. Right? The value of a squared is actually the pure constant. It doesn't matter if this is height or not. Okay, because we could actually rewrite this as 5 plus a squared. Doesn't matter. A squared is 5. Take the square root of both sides. Okay. A squared raised to 1/2. These two here cancel with this. Left hand side will just be simply a. 5 raised to the 1/2 is just the square root of 5. Okay. X squared is b squared. Okay. We just match this one here. This b here refers to this, and this e squared refers to 5. So in here, b squared is x squared. Then again, take the square root of both sides. B square raised to the 1/2, these two here cancel with this, left hand side, remaining term will just be simply B. X square raised to the 1/2, 2 times 1/2 is 1, so the square root of x square, it's a perfect square, it is just simply x, right? So V is x. Let's compute for dB. The differential of B is just dB, the differential of x is just dx, and it is exact. Right? It is exact. So our assumption that this problem or the solution of the second one is under arctangent was correct. So we just follow the formula for taking the differential or integral of arctangent 1 over a, arctangent of b over a plus c. So the final answer should be equal to, first one, we introduce 1/2, the integral 2x dx over x squared plus 5. This now falls under natural logarithm after replacing 1/2. Minus 5, it was outside, right? Minus 5. This is 1 over a. We are following the formula for arctangent, 1 over a. The integral of dx over x squared plus 5. So actually, 5 over the square root of 5 is just the square root of 5. So what will come out will be, this is 1/2. The integral of this will now be under natural logarithm of x squared plus 5. Okay? 5 over the square root of 5 is just the square root of 5. So I place it here, the square root of 5. And this falls under arctangent. So arctangent of B, what is B? It is x. And what is A? Is square root of 5 plus C. So final answer, 1/2 natural logarithm of x squared plus 5 minus the square root of 5, arctangent of x over the square root of 5 plus C. For 5 over the square root of 5, no problem, it's the square root of 5 times the square root of 5. Because the square root of 5 times the square root of 5 is 5, all over square root of 5. Right? So actually this cancels with this. So 5 over the square root of 5 is just the square root of 5. Okay? That's why this is the square root of 5. Or you could place it as 5 over the square root of 5. It doesn't matter. Right? So final answer, 1/2 natural logarithm of x squared plus 5 minus the square root of 5. Second one, arctangent of x over the square root of 5 plus c. That's the final answer. It's easy, right? Oh, I think, ladies and gentlemen, these are good examples for the integration of inverse trigonometric functions. I presented the arcsine solution and the arctangent solution, but as you notice it, the only problem is the verification of the value in B for you to follow the formulas. If it doesn't follow the formula after the verification of the value of A and B, your solution is wrong. But if it follows the formula, your solution is correct. Okay, ladies and gentlemen, this is not a viral video. This is an educational video. Okay? This is not just only a one-time happiness for us. Because in the long run, you will need this for those who are taking up integral calculus. Okay, so guys, if you like it, please click like. If you want to share it, please click share.